There we go. Okay, so we're in part one, what we did was we did first order. First order means first derivative. Okay, so first derivative is right here, and it didn't have to be linear. It didn't have to be linear. Okay, so, but now what we're doing is nth order. So nth derivative right here, nth derivative. Okay, and linear is for sure y and its derivatives on the left-hand side when you put it into normal form. And you have it to the first power and you divide through so that the leading coefficient is, a 1. Just to remind you, what did first order linear look like? Not all first order are linear, right? We had many different kinds. But remember this, y and the derivatives on the left-hand side. This is a 1, right? And then this is your forcing. That's a first order. First order, first derivative. Okay. Now, what are the coefficients? So the coefficients are these, right? So this is going to be a 1. So we just usually leave that off after we put it into normal form. So the coefficients are a1 of t, a2 of t, dot, 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 an of t. Okay. And then your forcing is the f of t. And when is it homogeneous? Remember, homogeneous when the forcing is absent. Forcing is absent. And non-homogeneous is when you actually have the forcing there, so that the forcing is not 0. Okay? So it's just like before. So we had first order linear, and remember we had homogeneous and non-homogeneous. Now, remember what a solution is. A solution is a function over an interval where y and all the derivatives that you need, because you need to, plug it in here, right? You want to be able to plug it in there, and all those derivatives are defined over that same interval. The coefficients of forcing are defined over the interval. And when you sub it into the equation, you have a true statement for all t in the interval. So really what it's just saying, left-hand side equal right-hand side. And notice if you have an initial value problem, okay, here it is. Here's the differential equation, right? And then now you have your initial condition over here. So here you have to have several of these, okay? So if it's nth order, typically the way we're going to number it is we're going to start off with y naught, y1, dot, 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 y, n minus 1. So since we're starting with 0, what you have is you have n initial values, okay? So one more time. The initial time is the ti, okay? And the initial data or the initial values are these guys. So there are n of them, because this one you start at 0, so then it would have been the nth one, okay? And the existence and uniqueness theorem is this, that if the functions, in other words, if the coefficients and the forcing are all continuous over this interval, no matter what your time is in the interval, and no matter what numbers are given as your initial data or your initial values, there exists a solution. Not only does there exist a solution, the solution is unique. And it's going to be thus, right? And so what that means is if you sub it in for the y's, you're going to get a true statement. And if you sub it in here, right, you're going to get, it satisfies the initial conditions. So then this solution has n continuous derivatives over that interval. And if these all have m continuous derivatives, then the solution will have at least m plus n continuous derivatives. So let's just go ahead and just practice very quick and see how we use this. What you do is you just want to figure out what is the interval of definition, right? So let's look at this. Can everybody see here? You have this differential equation. Same differential equation over here, but when you have your initial condition, here's your initial conditions right here. And if you have different initial conditions, it's a different initial value problem. So here's an initial value problem, and here's another initial value problem. Okay, same differential equation, just different initial value problems. Now let's go ahead and write down what is the interval of definition. So what we're going to do is we'll just go ahead and go like this, right? This is t-axis. And let's take a look at the differential equation. What don't you want? So here's this right here is
T equals 4 and -2.
right. So everybody see this? This is you just look at your forcing and you look at your coefficients, and you want to just see where are they continuous. And if they're pre-calculus, they're continuous where they are defined. In other words, they are continuous on their domain. And so over here, you just see, oh, well, you don't want it to be t equal 4 and -2. So here's 0, 1, 2, 3, 4. So you don't want this. So you pluck it out. So you don't want that. And you don't want it to be -2. So you pluck this out. Okay. All right. So what that says is that you have three potentialities. You have this one, or this one. Okay. So then what we do is we look over here. And so notice this is the initial time. This is your initial time. Okay. So we don't want -2, -4, but you look for your initial time, and that was the 0. So that's right here. This is your initial time. And it goes right here. Okay. And because of that, then you pick the biggest interval that it's in. That's this. So the interval of definition for this initial value problem is -2 to 4. Notice it goes left to right, less to more. If you wrote for -2, that's wrong, right? It always goes from left to right, less to more. Okay, then I'm going to be quiet. I want you guys to write down the interval of definition for the next one. And now, can somebody tell me what that's going to be?
From 4 to infinity.
Exactly. So this is this one, right? So does everybody see that this is the initial time, right? And if that's the initial time, then it's right here. And so what you have is 4 to infinity, okay? And so you just go interval of definition. You have 4 to infinity. There you go. It's so easy. I'm going to be quiet. I'm going to let you guys do this last one, okay? So why don't you do this one, and it's just going to take less than 30 seconds, I know. So I hope that everybody wrote this down. So third derivative, so it's third order. You got to put it into normal form. If you don't put it into normal form, all sorts of bad things will happen. Like you don't know the true forcing, you don't know the actual whatever. So everybody can see this, right? So then did everybody go ahead and say, okay, you look at your forcing and you look at your coefficient, right? And then you just go ahead, take out what it is. So you know it can't be the 0. So you pluck it out, right? And then what you do is you go ahead and you just look at, right? Here you go, -1. And -1 is on this side, right? So I'm going to go ahead and say this is your TI. So you can see that that's this guy right here. And so did everybody go like this? Did everybody write interval of definition? And did everybody say, hey, that's -infinity to 0? Okay. So that should be straightforward. So you should be practicing with linear. You only look at the definite. It's so easy, right? You just look at the forcing and you look at the coefficients. And look for where they're continuous. And if you're talking about pre-calculus, it's just where the domain is. So
I have two
that's
questions from this. One is, um, in all of these examples, they use the same value for t sub I. Will that necessarily be the case for
has
all
to
the
be
conditions?
that for an initial value condition, initial value problem, it's always the same TI. It always has to be.
Okay,
And,
and
and
then
if
the
it
other question
isn't,
I had
that's,
was,
yeah, go ahead.
um, how do we know that when we actually go to solve the differential equation, we won't have to use any kind of function that has an additional domain restriction, like a square root function or like a logarithmic function?
Can you say that again? I didn't hear you.
Yeah, how do we know that when we solve the differential equation, there won't be an additional domain restriction we're gonna have to add?
If you go ahead and you won't have to, because it will be very similar to the proof of first order. And if you go look at the first order, um, what you're going to find is that um, as we go along and we solve it, you'll see that solving linear is super, super, super easy. And when you go and you look at that proof, what we just needed was when we had the integration, we just needed to have the A and the F be continuous. That's all you will need. So you won't get something strange where you're going to have, where when you get your final answer, it will never be the case that when you get a final answer, you'll get something else, be, some other restriction. And as we solve this, you will see as we go on and solve linear differential equations, they are the easiest, and you will see what will happen. Okay. So within a day or two, you'll see what we get, and you'll see for yourself how easy it's going to be. And that's why we spend all this time on them, because they're the easiest ones. Okay. So why don't we go ahead and get started with that, and then you'll see for yourself. We're going to start with homogeneous. So homogeneous is the easiest, right? So let's go ahead and get the next thing out. And looking at this, remember what homogeneous means. It means forcing is absent. And notice that when you put it into when you put it into normal form, y and all its derivatives are on the left-hand side. Okay. And notice that you have a 1 right here. Okay. So you're going to have this. And what we want to do is we want to express it compactly. In the old days, you cannot believe it. I actually write this thing on the board and everybody would copy and then their hand would get really tired. All right. So now what we're going to do is we're going to write the derivative operator as d equal d dt. And this is the nth degree. Okay. So then an nth order linear operator is called that because it transforms a differentiable function into another function. So we're going to take a slightly different point of view. Okay. The idea is, can you see like right here? So what I'm going to do is rewrite that as this. And so you're taking the y over here, right? And then you can rewrite this guy as this. And notice how you write this as this. So you're taking the derivative. Okay. So now when you write it this way, can you see that what we're doing is what we're really doing is we're taking the nth derivative of this. So this is a fast, easy way, right? And then over here, you go like this, you just copy this down. But do you see this? You're taking the n minus first derivative of this guy. Okay, so when you write it down like this, the emphasis when you're thinking about this, so like this guy right here, you're taking the derivative of the y. And this you're just multiplying. So you can think of it as taking the 0th derivative of the y, so which is not doing anything. But then we have another way of writing this. So our convention is we're going to write it this way. When we write it this way, so notice I'm not writing any y's. We're going to write everything this way. What it means is we're going to take this whole thing and operate on the y to transform it. This 0 is not a 0 number. It is the 0 function. So does everybody see what this means? This over here means take the nth derivative of the y, take the n minus first derivative of y, and then multiply that with a1. Take the derivative of the y and then multiply it with this. And then just take the 0th derivative, which is not doing anything, and then multiply it with that. So when we write it this way, when we write this, we mean this, okay? So when we write this, but now our thought process is this is going to operate on that y to transform the y into the 0 function. It's a new way of thinking about it, because anytime you operate on a function, you're going to get another function out. So then what you're going to do is you write this whole thing is an operator. It's a linear operator. That's, you're going to write it as L of ty. That guy operates on the y to transform it to the 0 function. So y is a function. You can transform it to another function. Okay. So taking a linear combination of derivatives is an operator. An operator transforms, a differential operator transforms a differentiable function into another function. Okay. Now, sometimes, we have constant coefficients. So if you had, like this, remember the coefficients can be functions of t. But if we just had constant coefficients, like these are just constant numbers, like this, an, and this is just like above, and you're operating on this, you would write it this way. So you wouldn't write it with an L of t, you just go L like that. So that means these guys right here, these right here, these are not going to be functions. Well, you can think of it as constant function, but they're going to be constants, okay? So that is going to operate on the y and transform it to the 0 function. So now let's look at some facts. The derivative operator is linear. So what that means is when you take the derivative, right, of function 1 and function 2, you all know from calc, like this is probably, I don't know, the 4th week of class in calculus, something like that. It's like this, right? You can first add the functions and then take the derivative, or you can take the derivative and then add them together. But when you rewrite it, do you see that is the same as writing it this way? Everybody see this? This is the same as writing it this way. This is just nicer. This is just like less writing, right? And then notice also, do you guys remember when you take the derivative of a constant times a function, the constant can go out in front, right? So then this is another way to write that is d cy, and that is equal to take the derivative first and then multiply it by constant. Now, when you write it this way, if you've taken linear algebra, here you add and then you take the derivative, and then here you take the derivative and then you add. Here you you scale it by the constant, and then you take the derivative, and here you take the derivative and then you scale it. So this first thing is called, it preserves vector, this is preserves vector addition. Preserves vector addition. And then this is preserves scalar multiplication. So if you've taken linear algebra, vectors are more than just, arrows. They can be anything. So what you have here is, this is preserving addition and preserving scalar multiplication. Okay. And so the real background to differential equations is linear algebra, but we split it up into 2 courses. So, I don't talk about it that much. But the thing about this is linearity is preserving addition and scalar multiplication. Now, the kth derivative operator is the same. So it's actually the same thing with these guys, except that if you take the kth order derivative. So let me just quickly, stick it in. So this is if you take the kth order derivative, right? So you take the kth order derivative. So if you take the derivative k times, right, what happens is that you can scale and then take the derivative, the kth order derivative, or then you take the kth order derivative and then scale. Or over here, you can add two functions. Oops, you can add two functions and then take the derivative k times, or you can take the derivative k times. Oops, you can take the derivative k times and then add. Okay, so this is what this is. And of course, if you wrote it all out, you can write it this way. That means take the derivative k times after you had scaled it, or take the derivative first, k times, and then scale it. Here you would add the functions first and then take it, the derivative, or you can take the kth order derivative and then add it. Okay? Now, there's actually some work to do, but if you have L of t where you take all these derivatives of the y and then multiply appropriately by the coefficients right here, that whole thing is called a linear operator. And it turns out that your nth order linear operator is the same. It will also preserve scalar multiplication. So you scale and then operate, or you operate and then scale, or you can add the functions and then operate, or first operate them separately and then add it. Okay, so it preserves scalar multiplication and preserves addition. Okay, now what we want to do is we want to do this thing called method of linear superposition. And what it is when you combine solutions linearly, any linear combination of solutions, that is going to be a solution too. Now, what does that say? That's saying, say you have two solutions right here. Okay, what does that mean? That means if you take this guy and you plug it in here, you will get a true statement. Left-hand side will equal right-hand side. If you take this and you plug it in, you will get a true statement. So then if you scale, and then add, that's called making a linear combination, then that is going to be a solution too. In other words, you can take that guy and plug it in and you will get a true statement. Okay. And furthermore, if you have a whole bunch of solutions, that means any one of these, plug it in, you get a true statement. Take this guy, plug it in, you get a true statement. Left-hand side equal right-hand side. Plug it in. Left-hand side equal right-hand side. Then if you scale, and then add them all together, this will be a brand new solution. In other words, if you plug it in, it's going to be equal to 0. Let's quickly do that for two of them, okay? So remember, this guy right here, you can write it as L, this is written as L of t. You operate on a y to get 0, the 0 function, okay? So let's go ahead and prove it for 2. So let's say y1, y2 are solutions. So by concept of what a solution is, right? By definition of what a solution is, that means if you plug it in here, you get a true statement. So if you operate on the y1, you will transform him to 0. And if this guy's a solution and you plug it in, you get left-hand side equal right-hand side. So that means L of t y2 equals 0, correct? And now our goal is to show y equals c1 y1 plus c2 y2. So if you scale, and then add, that guy is going to be a solution too. So show is a solution too. So what you do is so how do you prove that somebody is a solution? Well, you want to plug it in and get a true statement. So that left-hand side equal right-hand side. So what you do is, let me go ahead, let me just put them right here. So this is another way to write it. Okay, so what we're going to do is we're going to say L of t, and you plug him in. Here's the y. And notice L of t. Okay, now we're going to write what the y is. It's this. So we're just rewriting it. So as everybody can see, y is you're going to scale it, and then add it. That's this. So this is, we're going to plug it in. We're actually plugging it in here, right? So there we are, right here. And then we're going to rewrite it. So this is what it is right here. Okay. And then remember, we just said that L of t is linear. So it's going to preserve vector addition. So it's going to go like this. So L of the first guy, L of the second guy. This is preserves vector addition. And then this is, now the C can come out in front, and that's preserve scalar multiplication. This is preserves scalar multiplication. And can somebody tell me what is this equal to? What is this guy equal to? By concept of solution, it was equal to 0. Right? And does everybody see this? What is that equal to? By concept of what a solution is, y1, y2 is a solution. So this becomes C1, 0, C2, 0. Does everybody see it's equal to 0? And do you now see what our goal is? Our goal was to show that this guy is a solution. So if we plug it in, he should be transformed to 0. Do you see that we just did it right here, and we show that it's equal to 0? Right? So therefore, it's a solution too. Okay? So what it's saying is, if you have a bunch of solutions of a homogeneous linear equation, then if you combine them, you go scale, 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 and then add them all together, that's going to be a solution too. Okay? So what we want to do is...
Oh,
yes.
sorry. Isn't that they're synonymous with each other, the vector and the scalar?
What do you mean synonymous? Okay, scalar means number. So scalar means, like, for us, it's a real number. Okay, and vectors are things like this, right? You know, so they're like arrows. But from linear algebra, vectors can also be functions. So the y1 and y2, they're functions, but functions also count as vectors too. So you have to take linear algebra. So I should just say preserve addition. So that would be less confusing. But in linear algebra, you learn that there are lots of different vectors, and it's not just something with magnitude and direction. It can be...
Yeah, that's why I was asking about that from linear. I just remembered something, so I thought it was synonymous. Yeah.
No,
Okay.
no, it's not synonymous. Vector is the objects in a vector space, and scalar is the number. Okay.
Okay.
All right. So let's go ahead and take a look at this. Okay. So here I'm just going to tell you, suppose you know that these guys are solutions of this differential equation. Look at all the derivatives. So it's a differential equation and it's equal to. Find constants so that this will satisfy the initial conditions right here. Okay, so we're going to do this thing called linear superposition. So let's first, I'm going to just break this down into bits and pieces. Okay, let's look at that differential equation. I'm going to recopy it right here. Okay, so I'm just going to recopy it. And so let's write it down. So it's y double prime minus y prime minus 2y equals 0. And what I want to do is I want everybody to watch. Okay, remember, when you take the second derivative, you can write it like this, right? Did I like do a lot of mistakes? Oh, I think I'm so sorry. Did you guys see the mistake that I did over here? I was tired. Did you see that I made a mistake right here? The K is supposed to go right here. My mistake. This was supposed to be TK. the TK, this is where you went. Why didn't somebody call me out? There we go. It's supposed to be like that. I don't know why I did that. Okay, so here we go. So let me write this out nicer. Okay, so this is this, and this is the derivative of y minus 2y equals 0. Okay, so this is writing it out using a different notation. Now, the other thing about this is, remember, you can always have that guy like this, right? So then when you write it this way, it's like this. Okay. And then can everybody see, you can also write it like this. I'm just writing the same differential equation like 5 or 6 different ways. You can write it like this. And you can just go ahead and label this guy to be your linear operator with constant coefficients. So if this was a t here and this is e to the t or something like that, then you would go L of t. But since the constants, this is -1 and -2, right? You can go L and go y equals 0. Okay. When you write it like this, here is the differential equations. This is the same differential equation. Okay. Different ways of writing it. But you can see that the emphasis now is L transforms the y into the 0 function. Okay. So we've got a couple different ways of writing this. I wanted to just go over this so that you guys understood that. Okay. We need to practice that because the differential equation can be given to you in many different ways. Next thing, what we want to do is let's double check that these are solutions. So this is going to be solution 1, and this is going to be solution 2. Okay. So let's say y1 equal e to the 2t. So what I want to do is I want to double check that it's a solution. Now, if we're going to take this guy, I'm going to plug it in here so that this is equal to 0. We need the first derivative, the second derivative, and that's all we need. So can you guys quickly tell me, what is the first derivative?
2e to the 2.
2e to the 2.
Second derivative?
4e to the
For e to the
2t.
t.
Yeah, and it's really good to go ahead and get them all done. Now what we're going to do is, here's the differential equation. So I'm going to plug it into the left-hand side, okay? So we're going to go ahead and we're going to say left-hand side equal, and then what we're going to do is we're going to plug it in and go y1 double prime, y1 prime minus 2y1. Does everybody see I took this and I plugged it in for the y? I plugged it in for the y, okay? That's the left-hand side. And next, we have what we did the work upstairs, so I can just copy this and plug them in. So all I did was I took these things and I plugged it in. And then you can see does everybody see? Let's go like this. And now, can you see that this is the left-hand side after you plug it in? And does everybody see it's equal to the right-hand side? And if the left-hand side equal the right-hand side, it's a solution. So that's how you double check, right? Left-hand side equal right-hand side. I haven't been like forcing you guys to do it, but you can always do that. Let's do that again, okay? So let's do it for y2. Copy down y2 and it is e to the negative t. All I did was I just took this and I put it here. Okay, and we're going to need the first derivative and we're going to need the second derivative. Can somebody tell me what is the first derivative and what is the second derivative?
Negative e to the negative t.
Perfect. Next one?
E to the negative t.
Perfect. And then what you're going to do is you're going to plug it into the left-hand side. So you're going to stick it right here. All right. So you're going to go e to the negative t. Oh, you know what? I'm going to write it out. Okay. I'm going to go y2 double prime minus y2 prime minus 2y. So then it's more clear. Okay. Then this was the pink after you stick it in. All right. And then you're going to go e to the negative t minus e to the negative t minus 2 e to the negative t. And you guys can see, can everybody see that this is going to be 1 minus a negative 1 minus 2? Factor out the e to the negative t. Do y'all see this is 0 e to the negative t? And this is going to be 0, right? And so then this is the blue. Left-hand side, oops, is going to be equal to the right-hand side right here, right? So I'm just going to go like this. Left-hand side, pink equal to blue. Okay? So does everybody see? That shows that these are solutions. By the way, look at the coefficients and the forcing. Where is that defined? Is it not defined anywhere?
All real numbers.
All real numbers. Interval of definition. All real numbers. You can write it like that and like that. Okay. So let's now do the next thing. Okay. You know they are solutions. So if you have a solution and you scale it, according to what we just did above, it's still a solution. If you have a solution and you scale it, multiply by a constant, that's still a solution. You have two solutions. If you add it, it's still a solution. So this is still a solution. Everybody get it? And so what we have is, our first one was e to the 2t. So it doesn't matter what number you multiply by, it's still a solution. And if you have e to minus t, multiply, it's still a solution. And then you put this all together, it's still a solution. Okay? So what we're going to do is we're going to figure out the C1 and the C2 so this is still going to be a solution. This is still a solution. But what we want to do is we want to find the special one that satisfies these initial conditions. So we have to find the C's right here. So what we're going to do is when you look at this, you have the original and you have a derivative. So what we're going to do is we're going to go ahead and take the derivative. So remember, when I do derivative, this is a y, right? But in reality, you all know this is y of t, and this is of t, right? But you can also just like write it like this. Okay, so now you guys tell me, what is the derivative of this one? What is the derivative?
2c1 e to the 2t.
Perfect. And what about this one?
Negative c2 e to the negative t.
Perfect. And remember, that was actually y of t, right? I didn't, this is y of t. This is y of t, right? You can write it, you can leave it off, or you just remember that it is. But like, look over here. Look, y of 0, y of 0. So what we're going to do is we're going to plug in 0. Okay? So we're going to plug in 0. Maybe what I'll do is maybe I'll make that red. I'm going to plug in the 0 right here. Okay? So we're going to plug in 0. So if we plug 0 in here and plug 0 in here, what's e to the 0? Okay.
Do 1.
So you're going to get, it's just 1, right? E to the 0 is 1. So does everybody see you're going to get C1 and C2? And what you're going to get is you're going to get 1. You're going to get 1, right? Okay. Now take the 0 over here and plug it in and plug it in. Now, what are you going to get?
2c1 minus c2.
Okay. Now I'm going to go ahead and put a 1 here, right? Because when you have minus, it's actually minus 1 times that guy. And remember what we have over here. This is y of 0 equal to 4, right? So this guy is going to be equal to 4, right? And then this is equal to 2. So does everybody see that's going to be equal to 2? All right. So I'm going to go ahead and write it equal to like this. This is equal to 4. And this is going to be equal to 2. Okay, so does everybody see that this is this, and here's the 4, right? And does everybody see that this guy is right over here, and then this is over here? Okay, so that's all we did. Now, this is very important. I want you, now I know you guys know how to solve for C1, C2. It's going to be easy, but I want you to do it using matrices because right now it's super easy numbers. And I want you to practice using the nice round whole numbers. And then later on, it'll be ugly, really ugly. But you will have practice and you know how to do it with matrices, okay? So what you want to do is notice that these are the coefficients. So what you're going to do is you're going to practice writing this as 1, 1, 2, -1, okay? And then you're going to go C1, C2. And then you're going to go 4, 2. Does everybody see? So this is also, you can write this equation as a matrix equation, okay? And the way it works is you go like this times this, plus this times this, so that's this part right here, equal that guy, okay? And then what you're going to do is you're going to say this times this, plus this times this is equal to this guy. And that is writing it as a matrix equation, okay? Then what you do is you're going to say this is matrix A, matrix A. This is X equal B. So this is AX equal B, okay? And then this is the trick. If your matrix A has, if your matrix A, so let me write it nicer. So AX equal B. If your matrix A has an inverse, you left multiply. Now with matrices, you cannot, like, if you had something like 3x equal 5, you can multiply this side by 1/3. So this is left multiply and this is right multiply. But with matrices, whenever you do anything, you have to left multiply both sides or right multiply both sides, okay? So if your A inverse exists, then you can do this, and this will be the identity. And then what you're going to get is X equal A inverse B. So first, you don't necessarily have a matrix inverse, okay? And the way you tell is, this is it. If the determinant of A has an inverse, then A has an inverse. And if A has an inverse, the determinant has an inverse. Now the determinant is this. The determinant of A is this guy. So you can often write, you write like this, you go A, B, C, D. You can write it like this, or you can write it as determinant A, B, C, D. Okay, so this is the notation. So if you don't want to write the word determinant, you have 2 lines. This does not mean absolute value. It means determinant. And determinant is multiplied this way positively, and then multiplied this way negatively. And that's your determinant, okay? Notice that this is a number. Now, what is the only number that does not have an inverse? What's the only number you cannot divide by?
0.
Exactly. So in other words, if the determinant does not equal 0, everybody else has an inverse. Only 0 does not have an inverse. If it's not equal to 0, then the A has an inverse. And so you have A inverse. And there's a formula for the A. The formula is this. It's 1 over the determinant. And what you do is you flip the main diagonal. You go D, A, and you have negative off the diagonal. So they stay the same. Only these two flip. Everybody else stays in their same place, but you make them negative. And you take this guy and you go scale, 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 scale. And that's your inverse, okay? And remember the determinant is AD minus BC. Okay, so that is the formula for this. So if it has an inverse, you can multiply on the left-hand side, and then this will go away. This will give you the identity. You get x equal A inverse B. So let's just practice. Tell me what is the determinant of the A? You multiply this way positively and subtract, multiply that way. Does anybody know what the determinant is?
-3.
-1. Subtract 2 times 1 is -3. And -3 does not equal 0. And so therefore it has an inverse. So, and what the inverse is going to be is it's going to be 1 over the determinant. That's why you need him not to be 0. Do you see? That's why you can't have him be 0, right? You want this guy not to be 0 right here, right? So you don't want him to be 0. And then what you do to write the A inverse is you flip the main diagonal. So take these two, flip them, and then copy down the 1 and the 2, but they have negatives in front of them. And this is what A inverse, this is the formula for A inverse, okay? And so you write this out and copy down the B like this. Technically speaking, what you're supposed to do is you're supposed to go scale, 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 scale. So then everybody would be multiplied by the -1/3, and that would be too many fractions. So you are allowed to go ahead and leave it in front and do it last. And always remember, now this is actually -3. The negative goes with the 3 because that's the determinant. But when you have a fraction, you know, if you have any fraction like this, A over B, that negative can be upstairs, it can be downstairs, or it can go out in front, okay? Now the negative goes with the 3 because it's a determinant, but now we're just going to use it. I'm going to put this right here. And now what we're going to do is we're going to go ahead and just write down the answer. So we're going to go this times this plus this times this. So you have -4 minus 2, and the answer is -6. And then you're going to do -2 times the 4 and 1 times the 2. So that's -8 plus 2, and that's going to be a -6. So now you only have to scale 2 times. You go scale, scale. And so your final answer is going to be 2, 2. And what is that 2, 2? Remember, what we're trying to get is we're trying to figure out the C1, C2, okay? And the C1, C2 is the X. So this right here is the final, that's what the X is, and this is the C1 and the C2. And now we finally figured out the answer. And so we're going to take the C1, C2 and put them in here. So let's write it out here. The final answer is Y equal, in fact, let me write it thick so you can see it. It's Y equal 2e to the 2t plus 2e to the -t. And this is your final answer. This is, remember, if you scale, this is a solution. We just showed, remember, we just showed that that was a solution. And we showed that this guy was a solution over here. So, but if you scale a solution, it's still a solution. If you scale, it's still a solution. If you add 2 solutions, it's still a solution. So this is a solution to the differential equation right here, and it satisfies this initial condition. Notice, if you plug in a 0, you're going to get 4. But then, now if you went ahead and took the derivative and then plugged in a 0, you'll also get this, okay? So everybody see how we did this? This is your answer. And now I want you to do the matrix method way, because right now it's easy and we want to practice easy. I know you know how to practice. I know you can just find C1, C2 on your own, like right here. Right, but practice the matrix way while it's easy, okay? Especially on all your quizzes. So practice it that way. Let's do that. Yes.
So you basically just want us to write the IC system as a 2 by 2 linear system and solve with matrices?
Yeah, a 2 by 2
Would it
matrix.
matter? Would it matter if we did I don't know, I guess like row reduction, like augmented
You
matrix?
can do row reduction augmented matrix, but I will tell you this is actually faster.
Okay.
But if it is bigger than a two equations and two unknowns, like if it was 3, then row reduction is the correct way to do it because it's the fastest way. So as long as it's 2 equations and 2 unknowns, this is faster than row reduction. If it's bigger than this, you have to use row reduction.
Okay, got it.
All right, so let's go ahead and practice this one, okay? Here's our differential equation. We've got some solutions. We want to find constants so that it satisfies this initial condition. So let's write down the differential equation just for practice, okay? So I want to write this down. I'm recopying the pink. Okay? So now what we're going to do is we're going to practice writing the differential equation. Let me go ahead. This is the second derivative. This is y equals 0. And you can see that you can also put that y over here. And so then this is the same as writing it this way. And you will sometimes have a question given to you in this way. And this means the top thing on top of it. So this is another way of writing the same thing. And then notice these are all constants. So you can write this as Ly. L transforms the y into the 0 function. So this is 5 different ways to write the same differential equation. Okay, we need to have the 5 different ways so that we later on we can do a little bit more with it. Okay, so now what we're going to do is we're going to practice double checking that these are solutions. Okay, so let's take a look at this. So let's write down the first one. And can you guys, looking ahead, you see you're going to need the first derivative and you're going to need the second derivative to plug it in. So quickly tell me, what is the first and second derivative?
-2 sine 2t,
Perfect. Next.
-4 cosine 2t.
Perfect. And now what you're going to do is you're going to go ahead and plug it into the left-hand side. Okay, so the left-hand side is left-hand side. When you plug it in, it's going to y1 prime 4y1. So in other words, you're going to take this guy and you plug it in here and you plug it in here. Okay, and then that's going to be, and you've already written down the answer. And then plus 4 cosine 2t. And look, you can just see that's going to be the 0, which is the right-hand side. So does everybody see that left-hand side is equal to the right-hand side? And if left-hand side equal right-hand side, you've got a solution. Okay, let's quickly do that. So can you guys quickly tell me what is the first and second derivative of this? All I did was I just copied.
2 cosine t
What else?
and -4 sine 2t.
Perfect. And now you're going to go left-hand side. And remember, you're going to take this y2, you're going to stick it in here, and you're going to stick it in here. So you go y2 double prime plus 4y2. Okay. And then what you're going to do is -4 sine 2t plus 4, and then you copy. Just so you're plugging everything that you did above. You can see this is going to be like this. And you can see, oh, look, the pink side is the left-hand side. And then that's going to be equal to the right-hand side. And when left-hand side equal right-hand side, there it is. Really quickly, you notice that the forcing is 0. And you notice that the coefficient is constant. These are all constant. So what is the interval of definition?
All real numbers.
Yep, all real numbers. Okay, and now you can say, okay, I've shown that y1 and y2 are solutions. So then what you would say is, well, if that's the case, if you have a solution and you scale it, it's still a solution. If you have another solution and you scale it, it's still a solution. And so now that, and when you add two solutions, it's a solution. So in other words, if you have, for instance, you have cosine 2t, that's a solution, and you scale it, that's a solution. Sine 2t is a solution, and you scale it, that's a solution. And when you add, it's still a solution. So there you go, that's a solution. Okay, so now what you're going to do is you're going to take that guy, all right, and what we're going to do is we're going to try to find, we know that this is going to be a solution. We know this is a solution, but we want to find the C1 and C2 so that we satisfy those initial conditions, okay? So let's look at this. So when you have the initial condition, you start with y, and then you go y prime, okay? So go ahead, tell me, what is the first derivative of this term?
Two C1, negative 2C1 sine 2t.
Perfect. Next guy. What's the derivative of this?
2C2 cosine 2t.
Perfect. Now remember, the y is in reality y of t. I mean, you don't need to write it down, but you could if you wanted to, right? So what we're going to do is we look over here and we say, what are we plugging in? We're not going to always plug in 0. You know, we could have plugged in some other number like 1, right? But let's use something easy here. So that's going to be 0. So we're going to plug in 0. So when you plug in 0 to cosine, you're going to get what? What are you going to get here? Yeah, 1. So you're going to get C1. And then what's the next one?
2C2.
When you plug it in,
Oh, 0.
exactly, 0. So I'm going to write 0C2. And let's go ahead and now plug in 0 right here. So we're going to plug it in here and plug it in right over there. And what are you going to get?
0.
0.
C1.
To C2. Okay. And then take a look at this now. So looking at this, you guys can see that this is this guy. And then we can go ahead and we're going to set it equal to 3. Right? And then you can see also that this is this. And you can set it equal to -2. Okay? So now we've got this. And actually, it's so easy, you know, it's so easy that we don't even need to do matrices, okay? You can see that C1 is going to be 3, and then the C2 is going to be -1. But let's practice. And the reason why I want us to practice is because while it's nice round whole numbers and super, super easy, you can just kind of quickly check your answer in your mind, right? And what I want to do is I want to go ahead and have us practice doing it with matrix methods while it's easy. And then later on, when it gets hard, you know, you already know how to do it, and then it's not that hard, okay? Because it can get really ugly. Like these are nice round whole numbers, but what if you had some ugly functions all the way through with t's all over the place? All right, so I just want us to do it when it's easy, okay? So with us, does everybody see this is matrix A, this is vector X, and this is vector B. Okay, so this is AX equal B is what this is. And then what we're going to do is you want to say to yourself, tell me what is the determinant of the A. What is the determinant of the A?
2.
This times this, subtract the 0, that's 2. And as long as it's not 0, A inverse exists. So if you have AX equal B, then what you do is you multiply both sides by A inverse, but it has to be left multiply. You can't do right multiply. This goes away, that's the identity, and you get X equal A inverse B. Okay, you can skip this and you just go ahead and write down the answer. So in the future, you don't even need to write all this over here. You can just go skip, right? And you're just gonna say A inverse B, but I'm just writing it out this one time, okay? So this is going to be equal to, so remember what the formula is. It's 1 over the determinant, and the determinant was 2. Then what you do is you flip the main diagonal, and then you copy down this, and you put negatives. But if it's 0, you don't have to worry about it, okay? So then you have this, and then copy down your B. And now, technically, you're supposed to go scale, 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 scale. But we like to save this guy for last because then you don't have as many fractions. So you're going to go 1/2. And then what you do is you go this times this plus this times this. So you always do row times the column. So then that is 6 plus 0. So that's going to be equal to 0. Let me go ahead and write it this way. And then you're going to go this times this, and this times this, and that's -2. And then that's just going to be -2. And then you can go scale, scale, and then it's going to be 0, -1, which is what we just said it was going to be. And remember what the goal was? The goal was to figure out who is the X, which is the C1, C2. So this is the C1, C2 right here. You can even write it real small. This is going to be the C1, this is going to be C2. And remember what the goal is. You're going to take the C1, C2, and you're going to plug it in here and here to write down your Y. So let's write down the Y now. You can find the final answer. Y equal, the C1 was 0, cosine 2t, and C2 is 1, sine 2t. And so you can also just write it down as Y equal negative sine if you wanted to, like this. And here we go. This is going to give us, did I make a mistake?
Yeah, I believe it was supposed to be 6.
That was supposed to be 6. I know, I was just like, wait a minute. Okay, hold on a second. Yeah, you're right. So that was a 6. What did I write 0? Or maybe I just got confused. I know I was confused. Okay, so here's the 6. And then what would that be? That would be a 3, right? Would that be a 3? I think that's a 3, right? So this was a 6. There we go. So then this is going to be 3. There we go. This is, here we go. Oh, whew. There we go. And if we plug in a 0, yeah, this looks right. Yeah, and I'm just like trying to do this in my head. Okay, yeah, this is correct. So this is your answer. So this is the particular one. So that when you plug, let me go ahead. When you plug in 0, you're going to get this. And then when you take the derivative and then you plug in the 0, you're going to get that. Okay. Now, you don't always are going to plug in 0. You might plug in a 1. So let's practice this one, okay? Let's do this one real quick. So this is fast. So here is our differential equation. Is this in normal form or not? Is that a normal form? Does everybody see it's linear, but isn't normal form? Yes or no?
No.
No.
No, because this is not a 1. So you can, now you're supposed to divide through, okay? But for right now, just to figure out whether it's a solution or not, you can go ahead and just say, well, I'm not yet going to do anything with the normal form. I just want to figure out if it's a solution, okay? So you can go ahead and go like this for now. But if you're going to do anything more, than figuring out whether it's a whether our solutions really are solutions, you need it in normal form. Okay, so I'm going to write the differential equation like this. Everybody see? So you should practice so that you understand all the different ways of writing down a differential equation. It's not hard. It's hardly anything. But just by practicing doing it this way, then it's really super easy. Now, do I write L or do I write L of T?
L of T.
Correct. So if it's not constant coefficients, then you write it this way. And now the concept is the differential equation is an operator acting on the y equaling the zero function. And so the pink, these are 5 different ways to write the same differential equation. Then you can also practice seeing are these guys solutions? So you can call this guy y1 and you can call this guy y2. Okay, so you go y1 is equal to t. And then now tell me, can somebody tell me real quick, what are the derivatives?
1 and 0.
Perfect. And then you go left-hand side, equal, and you can plug this in, and you would copy 1 plus t squared, y1 double prime, 2t y1 prime, plus 2y1, and then go 1 plus t squared, and look, this is the 0, 2t times 1 plus 2 times t. And you can see that this is going to be equal to 0, and that's the right-hand side. Okay, so that we have this is what this left-hand side, so when you plugged it in, and then what you get is that's going to be equal to the right-hand side. And if left-hand side equal right-hand side, correct. All right, and then over here, y2. Can somebody really quickly tell me what are the derivatives?
2t and 2.
2t and 2. Does everybody get what you're going to be doing? I'm going to go ahead and I'm going to skip so that we save some time. I just want to finish this up. Okay, so you're still going to go ahead, you'll plug it in, and then you're going to check the left-hand side equal right-hand side. And now, however, make sure you understand, right? If you're going to figure out the interval of definition, you need to put this into what? Normal form. Okay, so if you're going to check for interval of definition, you're going to look at this. And what do you see? Is there going to be any problem anywhere? No. So you're not going to have any problem anywhere. So interval of definition is still going to be minus infinity, infinity. Okay. And very quick. So now remember, whenever you have C1 times the first guy, the first solution, and C2 times the second solution, that is still a solution. And then what you're going to do is you're going to take the derivative. So this is C1. Can somebody tell me when you take the derivative here, what is that going to be? Does everybody see that? And then when you go ahead and you go here, what's the derivative of that? Zero, because that's a constant, okay? Now, the thing I wanted you all to see is that we're not always plugging in 0. Does everybody see over here, you plugged in a 1. So you can plug in a 1, for instance, okay? And then what you get is C1, and then this is 0, C2. This is C1, 2C2. And you still do the same thing. Here's the 3, right? So you can have this, and then this is going to be equal to the 3, right? So you have this is going to be equal to 3. And then similarly here, and then you have this, and that's going to be equal to the 1, right? And notice this is, let me go ahead. This is a 1, 0, 1, 2. Okay. So let's quickly, does everybody see you still do the same kind of thing? Very similar. Let me go ahead, finish this, and then we'll be done. Okay. So again, make sure you go 1, 0, 1, 2. And then this is going to be C1, C2. So you're solving for C1, C2. And it's going to be 3, 1. Okay. So that what you have is you have AX equal B. And this is 2 minus 0, and it's not equal to 0. So A inverse exists. So X equal A inverse B. Let's go ahead and write the X equal A inverse B up here. X equal A inverse B. So the inverse, is going to be 2 minus 0. So that's the bottom. So 1 over the determinant. Flip the main diagonal. You have the 0 and you have the 1, but you have negatives in front of them. But when you have a negative in front of 0, it's still 0. So that is A inverse right here. This is the A inverse, okay? So that's A inverse. And then copy down the B. The B is 3, 1. Now, technically, you're supposed to go scale, 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 but you're allowed to go ahead and save this for last so that you don't have that many fractions. So here, what you're going to do is you go row column. And what that means is 2 times 3, 0 times 1, and that's going to be 6. And you do row column, okay? So row column is like this. So what that means is this times this, negative 3, 1 times 1. So that's negative 3 plus 1, that's going to be 2. And now when you scale, you only have 2 things to scale and get 3, 1. And remember that the X was the C1, C2. So that's this. So you can just say, oh yeah, that was the C1, C2.
Professor,
then-
I think it was -2.
Oh, was it?
I mean, yeah.
Yeah, you're right. That was a -2. Thank you. Thank you. And then what you can do is you take the C1, C2 and you plug in here and here. And then what you get is Y equal 3t minus 1t squared minus 1. And that's your solution, so that this right here, will satisfy. First of all, you can see it's a solution. But now if you plug the 1 in, you're going to get your initial condition. And after you take the derivative, you'll also get this, okay? So does everybody see how to do that? Okay. So I think what I'm going to do is it's absolutely important that you see the last 2 examples. Absolutely important, because we're going to move away from the nice round whole numbers, okay? So I'm going to stop right here. Can you guys watch the end, the last 2 examples, all right? And then we're going to pick it up after the exam next Wednesday, okay? So review will be 7 o'clock Friday night at this link for an hour, and then I have to run at 8 o'clock. Okay. But hopefully everything will be okay. And we have a sample exam. It's going to be at that level, no MATLAB. And then the fastest and easiest way to understand everything is to rewrite all your quiz study guides. Then do homework 8, homework chapter 9, and then look at the sample exam. Okay. All right, guys. So I will see you Friday. Some of you, at least. Have a good one, and I'll tape it.
Thank you.